Algebraic structures, Lecture 9, Finitely generated abelian groups. Let's recall classification of finite abelian groups, which we did on the previous lecture. Theorem: every finite abelian group decomposes into a product of cyclic groups whose cardinalities are powers of prime numbers. Moreover, this decomposition is unique up to permutation of factors. In other words, every finite abelian group is isomorphic to the following group. So we take the cyclic group of order p1 to the power k1, where p1 is a prime number, and then we take the Cartesian product with another cyclic group of the order p2 to the power k2, and so on. We have finitely many factors in this product. Moreover, if we have two such decompositions, so zp1 to the power k1 times zp2 to the power k2 times and so on, is isomorphic to zq1 to the power r1 times zq2 to the power r2 times and so on, with all qi and qj primes and all ki and rj positive integers, then the number of factors is the same, so m is equal to n, and there is a permutation sigma in Sm such that Qi is equal to P sigma of I and Ri is equal to K sigma of I for all I. So this was the main result of the previous lecture. In this lecture, we will extend this result to the case of finitely generated abelian groups. And to start with, let us talk about free finitely generated abelian groups. Let k be a positive integer, and consider the abelian group z to the power k. For each I between 1 and k, denote by ei the element of z to the power k, which has 0 everywhere except for position I, where this element has 1. Let E be the set of all these ei's, so e1, e2, e3, and so on up to ek, and this is a subset of z to the power k. Of course, it depends on k. Theorem: for any abelian group G and any map F from the set E to G, there is a unique group homomorphism phi from z to the power k to G, such that phi of ei is equal to f of ei for all I. This theorem means that the group z to the power k is free as an abelian group over this set E. So if we look at our notion of free group, we have exactly the same property but restricted to the class of abelian groups. Terminology: the set E is usually called the standard basis of this group z to the power k. Let us prove this theorem. We start with the following observation. Every element in z to the power k can be written uniquely as a linear combination of the elements of the standard basis with integer coefficients. That's an obvious observation. Now let G be a multiplicative abelian group with identity E, and let F be any map from our standard basis E to G. We define the value of our homomorphism phi at such a linear combination at the sum of ai ei, where I is from 1 to k, in the following way. We take f of e1 and take it to the power a1, then we take f of e2 to the power a2, and so on, and we multiply all these values. Directly from the definition, we see that this is a group homomorphism. And also, since our standard basis generates z to the power k, it means that this is unique. So there is a unique way to extend f of ei's to this homomorphism. And this completes the proof of our theorem. Next, let us compare z to the power k with z to the power m. So let k and m be positive integers. Proposition: then the fact that z to the power k is isomorphic to z to the power m as a group implies that k is equal to m. Proof: Assume that k is greater than m and let phi be an isomorphism between z to the power k and z to the power m. Then we have the standard basis e1, e2, and so on, ek in z to the power k, so we can consider the images of the standard basis elements inside z to the power m under this isomorphism. So let's call them f1, f2, and so on, fk. So fi is the image of ei under phi. So these are elements in z to the power m, and z to the power m is a subset of q to the power m, of the m-dimensional vector space over the field q. Since k is greater than m by our assumption, we have k elements in an m-dimensional space, so they must be linearly dependent. That's a basic linear algebra statement. Of course, this linear dependence is over rational numbers, but if we multiply with common denominator, we get a linear dependence over integers. So we have a non-trivial linear combination, sum I from 1 to k, coefficients ai times phi of ei, for some coefficients ai not all equal to 0, and this linear combination is equal to 0. But phi is a homomorphism, so we can move it out and write that phi applied to the element sum for I between 1 and k ai ei, that's an element now in zk, so phi of this element is equal to 0. But by the observation from the previous slide, this element sum over I from 1 to k ai ei is a non-zero element of z to the power k. But then this means that our phi is not injective. And this leads to a contradiction which proves our proposition. Now we can formulate the main result of today's lecture, which is a classification of finitely generated abelian groups. So, theorem: every finitely generated abelian group decomposes into a product of infinite cyclic groups and cyclic groups whose orders are powers of prime numbers. Moreover, this decomposition is unique up to permutation of factors. Please note that the only infinite cyclic group is Z, so a product of infinite cyclic groups is exactly Z to the power k, which we studied on the previous slides, and our main result asserts in particular that the number of factors isomorphic to Z does not depend on the decomposition of our finitely generated abelian group. And one can compare this with the result established on the previous slide, that z to the power k is isomorphic to z to the power m, if and only if k is equal to m. So that's a part of this main result. So the remainder of the lecture is devoted to the proof of this theorem. And we start with looking at quotients of z to the power k. Proposition: any finitely generated abelian group G is isomorphic to a quotient of some z to the power k. Proof: let X be a non-empty finite generating set for G, and let K be the number of elements in X. By the free property of our free abelian group z to the power k, any bijection from the standard basis of this group to X extends to a group homomorphism phi from z to the power k to G. This homomorphism is surjective because X generates G, and in particular, G is isomorphic to the quotient of z to the power k by the kernel of this homomorphism due to the first isomorphism theorem. So every finitely generated abelian group is a quotient of some z to the power k. So we need to understand quotients of z to the power k. In order to understand quotients of z to the power k, we need to understand subgroups of z to the power k, because that's what we quotient out when we take the quotient. Proposition: any subgroup of z to the power k is isomorphic to z to the power m for some m less than or equal to k. Proof: let us do induction on k. If k is equal to 1, we are talking about subgroups of z, of the cyclic group, of the infinite cyclic group. And so the claim just reduces to the claim that every subgroup of a cyclic group is cyclic, which is a straightforward thing to prove using Euclidean algorithm. So now assume that k is greater than 1, and let psi from z to the power k to z be the homomorphism given by projection onto the last component of the vector. So if you take an element a1 and so on ak from z to the power k, psi sends this element to the last component ak. That's of course a group homomorphism. The kernel of psi consists of all elements of z to the power k in which the last component is 0. And of course this kernel then is isomorphic to z to the power k minus 1. Now let H be a subgroup of z to the power k. If H is a subgroup of the kernel of psi, then we can use the inductive assumption and conclude that H is isomorphic to z to the power m for some m less than or equal to k minus 1, and we are done in this case. If H is not a subgroup of the kernel of psi, then psi of H is a non-trivial subgroup of the group of all integers. And the group of all integers is a cyclic group, so a non-trivial subgroup is also cyclic and it has a generator. So let little h be an element in our capital H such that psi of h generates the image of psi. Denote by k the intersection of h with the kernel of psi. Again, by induction, k is isomorphic to z to the power m for some m which is less than or equal to k minus 1, because the kernel of psi is z to the power k minus 1. Let bold k be the preimage of the standard basis of z to the power m under our isomorphism. Then send in the first m elements of the standard basis of z to the power m plus 1 to this bold k, and the last element of the standard basis to h extends to a homomorphism from z to the power m plus 1 to h. This homomorphism is surjective because our bold k generates k, which is the kernel, and our little h generates the quotient. So if you can generate the sub and the quotient, we generate the whole thing. Moreover, this homomorphism is injective because the elements of k together with h are linearly independent over q by construction. Therefore, this is an isomorphism which proves our statement. Now we can describe all different bases in z to the power k. Definition: a subset x in z to the power k is called a basis, provided that each element of z to the power k can be uniquely written as a linear combination of the elements in x with integer coefficients. So for example, the standard basis bold E is a basis of z to the power k. Proposition: all bases in z to the power k have exactly k elements. Moreover, a collection of k elements of z to the power k forms a basis if and only if the determinant of the corresponding coefficient matrix is plus or minus 1. Proof: let x be a basis of z to the power k which has exactly m elements. Then any bijection between this x and the standard basis of z to the power m gives rise to an isomorphism between z to the power k and z to the power m. And hence k is equal to m by one of our previous results. In particular, x is a basis if and only if any bijection between x and the standard basis in z to the power k gives rise to an automorphism of z to the power k. Alternatively, we can reformulate it in the following way. So this automorphism is given by the linear map, which sends an element x to the element sx, where S is the coefficient matrix of the elements in X. And we know from linear algebra that this is invertible if and only if S is invertible over the integers. So it's an invertible and as a linear map if we say extend scalars to rational numbers if S is just invertible, but in order for it to send integer vectors to integer vectors invertibly, it must be invertible over integers. So the inverse must have the same property. And over the integers, the only invertible elements are plus and minus 1, so the corresponding determinant must be plus or minus 1. And this completes the proof. Next, let us discuss the notion of a torsion subgroup. Let G be an abelian group. Denote by T of G the set of all elements of G which have finite order. Proposition: T of G is a subgroup of G. Proof: the identity belongs to T of G because the identity has order 1 and that's a finite number. Next, if an element A has order k and an element B has order m and both k and m are finite, then AB to the power km can be written as a to the power k to the power m times b to the power m to the power k. And this is equal to the identity to the power m times the identity to the power k, which is the identity. And of course we can do this only since our G is abelian, so we can permute A and B in any order we wish. But this means that the order of the product AB divides the product of k and m, and thus is a finite number as well. And so T of G is closed under the group operation in G. Finally, if an element A has order k, which is a finite number, then A inverse is by definition equal a to the power k minus 1. But then A inverse to the power k can be written as a to the power k times k minus 1, which is the identity because A has order k. And this means that A inverse has an order which divides k and k minus 1. So it's also a finite number. So this proves that T of J is a subgroup of G, and the subgroup is called the torsion subgroup of G. Next, let us talk about torsion subgroups of finitely generated groups. So let G be a finitely generated abelian group. Proposition: then the torsion subgroup of G is finite. Proof: we know that G is a homomorphic image of some z to the power k. Let H be the subgroup of z to the power k, defined as the full preimage of the group T of G, that's a subgroup of G, under this surjection. So we fix this surjection and we look at all elements of z to the power k which go to T of G. That's of course a subgroup. Then, by one of our previous results, the subgroup is isomorphic to z to the power m for some m which is less than or equal to k. In particular, it is finitely generated. But then it surjects onto T of G, which means that T of G is finitely generated. So now let A1 and so on Am be a finite set of generators of T of G, and R1 and so on Rk be their corresponding orders. Then any element of T of G can be written as a product of powers of generators, but we have finitely many generators, and each of them has only finitely many different powers, because they have finite order. So in total we have finitely many elements in T of G. And this completes the proof. Next, we need to discuss the notion of a torsion-free group. Definition: an abelian group G is called torsion-free, provided that T of G is trivial, so the torsion subgroup consists just of the identity element. For example, the trivial group is torsion-free by definition. The second example, each z to the power k is torsion-free. The third example, the additive group of all rational numbers is torsion-free. And the fourth example, a finite abelian group is torsion-free if and only if it is trivial. Proposition: for any abelian group G, the quotient of G modulo its torsion subgroup is torsion-free. Proof: assume that little g is an element in G such that some power g to the power k belongs to the torsion subgroup T of G. But then some power m of g to the power k is equal to the identity. But this means that G has finite order, the order of G divides km, and so already G belongs to T of G. And this proves our proposition. Now we are heading towards the proof of the main result of this lecture. First, let us discuss existence of the decomposition. Proposition: let G be a finitely generated abelian group. Then G is isomorphic to the product of some z to the power m and the torsion subgroup T of G. Proof. We know that our G is a homomorphic image of some z to the power k. And by the first isomorphism theorem, G is isomorphic to z to the power k modulo the kernel of the corresponding homomorphism phi. We also know that the kernel of phi is isomorphic to z to the power m for some m. So in particular, this means that we have a homomorphism from z to the power m to z to the power k, and we are interested in the cokernel of this homomorphism. A homomorphism from z to the power m to z to the power k is given by an integer matrix with k rows and m columns, and this matrix is defined as a coefficient matrix for the images of the elements of the standard basis of Zm under phi when we write them in the standard basis of z to the power k. And the freedom which we have is that we can change bases both in the original group z to the power m and in the target group z to the power k. And the base change means that we can multiply our matrix M, which determines our homomorphism, with invertible matrices both on the left and on the right. Multiplication on the left means base change in z to the power k. Multiplication on the right is a base change in z to the power m. So that's a basic linear algebra. So the question is, what is the easiest form to which we can reduce our matrix M using such operations? And the answer is given by the so-called Smith normal form. Theorem: for any integer matrix M, there are invertible integral matrices S and T, and they are invertible over the integers, so with determinant plus and minus 1, such that the matrix SMT is diagonal. So it has the following form. We have something on the main diagonal, the elements which we call D1, D2, D3, and so on. They can be 0 as well, but the rest is 0. So how to prove this? It's similar to the usual linear algebra argument. So multiplication with invertible matrices corresponds to sequence of elementary row and column operations. So we can swap row and columns, we can change sign in row and columns, we can add a multiple of some row to a different row, or similarly for columns. And using these, we can basically do an integral version of Gauss elimination. So the problem is that we cannot divide by integers in general, but just adding and subtracting, we can do Euclidean algorithm. So starting from the first column, say, we can do elementary row operations to create the greatest common divisors of all elements in the first column, and then we can proceed with the elementary row operations to make all other elements in this row to be equal to 0. And then we do the same thing in the second row and so on, and with all columns, and we get this form. Now we can complete the proof of our proposition. So we start with a group homomorphism from z to the power m to z to the power k, which is given by some matrix. We reduce that matrix to the Smith normal form, so we have a homomorphism which is given by a diagonal matrix. But if we have a diagonal matrix, then the cokernel of this homomorphism is very easy to describe. It's just the product of, so for each diagonal element, we take the quotient of z modulo this element times z. And that's a cyclic group. So the cokernel of our homomorphism is isomorphic to the product of cyclic groups. And then there are infinite cyclic groups here and finite cyclic groups, and the torsion subgroup is exactly the product of all finite cyclic groups in this decomposition. And this gives us the decomposition as claimed in the formulation of our proposition. Finally, we need to discuss uniqueness. If we can write a finitely generated abelian group G as z to the power m times the torsion subgroup of G, then we can factor out this torsion subgroup and conclude that z to the power m is isomorphic to G modulo the torsion subgroup. But this means that m is uniquely determined because we know that z to the power m is isomorphic to z to the power k if and only if k is equal to m. So this gives us that the torsion-free part in our decomposition is uniquely determined. But the torsion part, we already established that the torsion part is a finite abelian group, and uniqueness of decomposition for finite abelian groups was established during the classification of finite abelian groups. So together with the fact that the torsion-free part is uniquely determined, we complete the proof of the main theorem. So we establish that the decomposition in the main theorem is indeed unique up to permutation of factors. Here is an example. Let phi be a homomorphism from z to the power 2 to z to the power 3, which is given by the matrix 6, 8, 0, 8, 12, minus 24. Decompose the cokernel of this homomorphism into a product of cyclic groups as given by the classification theorem. Solution. Let us use elementary row and column operations to reduce our matrix to a diagonal form, to the Smith normal form. So first of all, we can kill this 12 using this 6 by subtracting twice the first row from the third row. And we get the matrix 6, 8, 0, 8, 0, minus 40. And now we can use the second row, 0, 8, and this 8 to kill this 8. So we subtract row 2 from row 1. And we can use this 8 to kill this minus 40. So we multiply row 2 with 5 and add to row 3. And we will get the new matrix 6, 0, 0, 8, 0, 0. And this is a matrix in a Smith normal form. So now we can read off the decomposition for our cokernel. So this 6 gives us the factor z divided by 6z. This 8 gives us the factor z divided by 8z. And since there is nothing here for the third element in z3, we will just have the free factor z. Now note that 8 is a power of a prime, it's 2 to the power 3, so z modulo 8z will be just the factor z8, but 6 is 2 times 3. So z6, which we have here as the first factor, should be further decomposed as z2 times z3. And so the answer is that our cokernel is the finitely generated abelian group, which has the following decomposition. So we have z2 times z3 times z8 times z. And this completes the solution. Some problems and questions at the end. Problem question 1. Check all the details in the proof of freeness of z to the power k as an abelian group. Problem question 2. Formulate the main result of this lecture, the classification theorem, for finitely generated abelian groups in detail using explicit decomposition and their comparison. Problem question 3. Prove with all details that every subgroup of a cyclic group is cyclic. Problem question 4. Prove the theorem about the Smith normal form with all details. And problem question 5. Prove that the automorphism group of z to the power k is isomorphic to GLK over Z. Thank you very much and see you next time.